right, as we approach the last major section of chapter 5, this whole part of this chapter is dealing with inequalities. So today should be pretty much all review, but we need to know and refresh our memories of this before we can move on. So an inequality says that two values are not equal, and there are other special symbols that show in what ways they are not equal. So remember, if I say A is alligator, if I make an L with my hand and turn it slightways, that makes a less than symbol. So that's A is less than B. If I put the line underneath it, that would be A is less than or equal to. And if I have the alligator biting the left, that'd be A is greater than B. And again, if I put my line underneath the greater than symbol, then that would be greater than or equal to. All right, so if we're solving one variable inequalities, these only have one variable, and it's usually an x. So here are your steps. Solve the inequality as you would solve a linear equation. And the one big thing you have to remember is if you divide by a negative number, you must flip the inequality symbol. Solutions will be graphed on a number line. We're going to call these boundary points, and then you will need to shade. And a greater than or less than symbol, you put an open dot. And if you have the equal to, less than or equal to, or greater than or equal to, then you have a closed dot. Just like we've talked about with domain and range, things like that before. Open dot means not equal to, closed means it does touch and equal. Then you can pick a test value located on a region on either side of the boundary point. And plug that into the original equation. And just remember, a true statement means to shade the region where the test point is located, and a false statement would mean to shade the region opposite to the test point. So let's go ahead and look at a couple of these. Example 1. All right, when you're doing linear inequalities or one variable inequalities, it is probably best to have the x on the left. And I'll tell you why in a second. So the first thing I would want to do is combine my like terms. And now I'm going to get my x's on the left, numbers on the right. So I'm going to subtract 6 and subtract 5x. So we get negative 3x is less than or equal to 6. And when I divide by negative 3, I get x is greater than or equal to negative 2. So remember, I divided by a negative, so I flip my inequality symbol here, and a positive divided by negative is negative. So that's my algebraic solution. I still need my graphic solution, and the reason why I want to put my x on the left is because once I put my closed dot on negative 2, I can just read the inequality and shade the correct way. So if this is saying x is greater than or equal to negative 2, where my value is greater than negative 2, well, the greater side is going this way. Also, you can kind of see the inequality is pointing to the right. That's the way we're shading. All these values are greater than negative 2. All right, for number 2, we want to distribute that negative sign. And again, it is easiest and probably best if you try and get the x's on the left, numbers on the right. I am going to combine my like terms here. So that'd be negative 4x minus 1. Oop, error here. Just distributing a negative sign through, so that'd be minus 1. So that's minus 1. So 3 minus 1 is positive 2. It's greater than or equal to 5x minus 25. All right, I'm putting my x's on the left, constants on the right. And that would give us negative 9x is greater than or equal to negative 27. I'm going to divide by negative 9. I'm going to have x, flip my inequality again, because again I'm dividing by a negative. That'd be positive 3. So that's my algebraic solution. I'm going to put a closed dot on 3. And again, this is saying x is less than 3. So my lesser y values are going this way. And you can also notice that kind of the arrow is pointing to the left. I'm shading everything to the left. These would all be solutions, all make a true statement. For example 3, we have our compound inequality, kind of like when we would write it for domain and range. To solve this, just pretend the left side's not there. To get the x by itself, you'd subtract 1 first. Now, you just have to remember that you have kind of 3 sides now, so you have to subtract 1 from every single side. So that'd be negative 4 is less than or equal to 2x, which is less than or equal to 8. And then again, if I didn't have this, to get the x by itself, I would divide by 2. And I would divide everything by 2. So I'd have negative 2 is less than or equal to x, which is less than or equal to 4. Now the x is by itself. So this is my algebraic solution. And this is saying x is in between negative 2 and 4, including negative 2 and negative and 4. So I'd have a closed dot on 2, a closed dot on 4, and my shading is in between, because all these numbers in between would fall into that. For example, 0. 0 is greater than or equal to negative 2, and then 0 is less than or equal to 4. All right, then we also have this OR inequality. The OR inequality, we're just going to solve 2 separate ones, but at the same time. So I'm subtracting 4, and then dividing by 3. So I'd have x is less than or equal to 2. I need to keep that OR. I'm going to divide by 5 for my second inequality. X is greater than 9. That is my algebraic solution. So I'd have a closed dot on 2, an open dot on 9. So 9 is off my graph here. I'm just going to extend this, put a 9 here with an open dot. So I want x to be less than 2. That's pointing this way. And or x is greater than 9. So that's going to be going to the right. And we'll get into those more later on. But bottom line, your solutions are in this area or this area. Can't be in both. That's why you have the or there. All right, so that's the one variable inequalities. Again, should mostly have been reviewed there for the 2 variable linear inequalities. First thing you want to do is make sure the inequality is in y equals form. If not, undo everything to get the y by itself. You want to graph the inequality on an xy coordinate plane using the slope and the y-intercept. Because again, these are going to be lines for now. Instead of the open dot, closed dot, if we have less than or greater than, we use a dotted line. And if we have the equal to, then we use a solid line. You want to look at the... All right, so let's do that first. So here we have 2x minus 1. And I'm going to start at 0, negative 1, and go up 2 and over 1. And then I'm going to go down to left 1. And since I have a greater than and it's not equal to, I have less sign, so I'm going to use less line. I'm going to use dotted line here. That's kind of how I remember it. Less sign, less line, more line. All right, now we get into step 3. Look at the y-intercept. A greater or greater than or equal to means to shade the greater or larger y values, where a less than or equal to means to shade the lesser or smaller y values. So here's our y-intercept. I have a greater than symbol, so my greater y values need to be shaded. My greater y values are up here, my larger y values are up here. So So everything on this side of the line needs to be shaded because that's where my larger y values are. For this one, again, these two, the y are by themselves already, so we're kind of done. So step one, we don't have to do that. Just remember, if it's in standard form, you would have to get the y by itself. So we're starting at 3, and then I'm going down 1 and over 2. And up 1 and left 2. And this has more sign, so more line, meaning I have to connect them, or if you have a line underneath, it is a solid line. All right, so then I have a less than symbol. So I look at my y-intercept. Where are the lesser y values? The greater y values are up here. The smaller values, y values are down here. So I need to be shading this way. All right, and then last thing we want to look at is the meaning to solutions. Any point in the shaded region is a solution to the inequality. To solve an inequality using the graph means to pick a number or point in the shaded region. To check if a number or point is a solution algebraically, you must substitute the x value in for x and the y value in for y. If it makes a true statement, the ordered pair is a solution. All right, so it says for the inequalities above, use the two graphs to state 2 points that are solutions. So I'll kind of split this right down the middle, left side, right side. So if we're looking at, using the graph, anything in the shaded region is a solution. So I could say 0, 2. I could say negative 6, 6. Anything on the dotted line is not a solution. If it's on a dotted line, that would be like, give you something like 6 is less than 6, which is not true. Whereas here, again, I can say 0, 0, 5, negative 2. But since this is a solid line, I could also say anything on the solid line because I would end up with something like 5 is less than or equal to 5, where, yes, it is equal to, so that works. Then the algebraic check says for the inequalities above, algebraically check if the point 2, 1 is a solution to each inequality. So, again, 2, 1, x, y. So my first inequality was y is greater than 2x minus 1. So I'm going to plug a 1 in for y, a 2 in for x. And we are trying to see if it makes a true statement or not. I get 1 is greater than 3. 1 is not greater than 3. That's false. So 2, 1 is not a solution. For our second inequality, again, that was y is less than or equal to negative 1/2 x plus 3. Same thing, I'm going to plug 1 in for y and 2 in for x. And I end up with negative 1/2 times 2 is negative 1. And I get 1 is less than or equal to 2. And that is true. So we'd say 2, 1 is a solution. And there's our review of inequalities.